Okay, so we are interested in finding the length of curves both in R2 and in R3. So to simplify things a little bit, I'm just going to derive this, and I'm going to start with a 2D curve, and then we'll be able to extend arc length in 2 dimensions to arc length in 3 dimensions. So let's suppose that we have a curve C that's parametrized by a vector function r of t, and we want to find the length of the curve from t equals a to t equals b. So here I've just drawn a general curve, and let's suppose that t equals a results in a vector that points to that point, and maybe t equals b is over here. So how do we find the length of the curve that goes from those 2 points along the curve? We're going to do very much like we did in Calculus 2. I'm going to break this up into pieces, into intervals, and one interval, I'm going to zoom into that interval and think about approximating the length of the curve in that interval with a straight line. So let's suppose that I've zoomed into this interval. So here's the curve, and we're very zoomed in into maybe t sub k and t sub k plus 1 interval. So I'm going to call the length of this line, I'm going to call it S. And the change in x along the horizontal change between the 2 points, we're going to call that delta x. And the vertical change between the 2 points, we're going to call that delta y. And here we can apply the Pythagorean theorem and get the length of the straight line. So the key idea here is that we're not getting the length of the curve. We're getting lengths of pieces of lines, line segments. And then when we make the intervals infinitesimally small, we're going to be able to approximate to get the exact length of the curve, because our line is going to get infinitely close to the curve itself. But let's set it up this way. So we can see here that the length s squared would be equal to delta x squared plus delta y squared, and this is just by the Pythagorean theorem. So the length of that line segment would be the square root of this delta x squared plus delta y squared. Now remember that when we've parametrized the curve, we're using an independent variable t. So it would be really nice to be able to express the changes in x and the changes in y. Each of those depends on how t is changing. So I'd like to be able to think about t as being the driving variable that affects a change in x and also affects a change in y, or results in a change in x and results in a change in y. So what I'm going to do is to help us understand that is, or to help us see that in the equation, is inside of the square root, I'm going to multiply by delta t squared over delta t squared. So each of the 2 terms, so I'm multiplying by 1, which means I'm not changing anything inside of the root. So I haven't changed anything. I would just like to see how the change in x, the horizontal change, is affected by a small change in t, and how a change in y is affected by a small change in t. So now we can see here that if I distribute delta t squared over delta t squared, I'm going to leave 1 out here, the numerator, but I'm going to distribute 1 over delta t squared throughout the sum inside the square root. So this is going to give me delta x squared over delta t squared plus delta y squared over delta t squared. And so this just gives us an approximation to that length of that line segment. Now, we can get better and better approximations if we let delta t get very, very, very small. So if we do that, when we do that, and delta t gets really small, we can apply the mean value theorem that tells us that the quantity here, delta x over delta t, and the quantity here, delta y over delta t, will at some point in the interval delta t there will be a place where that quantity, the average rate of change of x and the average rate of change of y, is equal to the derivative of x and the derivative of y as delta t gets very small. So how are we going to deal with this? Well, let's suppose that first I'm going to add up all the pieces, right? So this is just one little piece. When we add them all up, we would have a sum, right? If we're adding from t equals a to t equals b, we would have a sum with some index, maybe from I equals 1 to n, because we're adding, let's say, n pieces of this quantity. And I'm going to write this again as delta t squared. And inside the brackets here, I'm going to have delta x over delta t, and this is quantity squared, plus delta y over delta t quantity squared. Now, in this sum, that would give me an approximation to the length of the curve. We're going to pull out that delta t, because the square root of delta t squared is just delta t. And now we have the square root of delta x over delta t squared plus delta y over delta t squared. Now, when I've added all of these things up, if I take the limit of this sum, so I'm going to just call this capital S for now, since we've just added up all those segments. I'm interested in the limit as delta t goes to 0 of this sum from I equals 1 to n of delta t. I is an index because we could assume that some of the lengths of the intervals are different lengths, and we could have a delta t sub I, but I'm being a little bit general here. And so what happens here when we take the limit is we're going to have an integral from a to b. We're going to get the exact length of this curve. Call it maybe capital S or L, or whatever you want to call it. And delta t, as it becomes infinitesimally small, that's going to be our dt. And as I mentioned earlier, we can apply the mean value theorem to each of these quantities in each subinterval, but that's just going to be the derivative dx dt squared as delta t gets very, very small. And as delta t gets very small, for the delta y over delta t, we're going to have a dy dt squared. So now we're dealing with infinitesimal changes in x and y with respect to an infinitesimal change in t. And this is what we call the length of the curve from a to b. Now, one thing to note here is we've got derivatives inside. Recall that our curve, our parametrized curve, is x of t, y of t. And if we think about, well, this looks a little bit like the derivative of our curve. So the derivative of our curve will be x prime, or dx dt, dy dt. So if you notice what we have, the quantity that we have over here, you've seen this before. The square root of components squared, that's the magnitude. So that quantity, the magnitude of r prime of t, is just the square root of each of these derivatives squared and added up. And so we have a more abbreviated way that we can write the length of our curve. I'll do it in yellow. Let's call it S or L, whatever you want to call it. We have integral from a to b. And now this is just going to be the magnitude of the derivative of our vector function times infinitesimal quantity dt. And this is the length of a curve, which we also called arc length. That's from t equals a to t equals b, also called arc length.